All right, thank you very much. Bear with me, just two more talks. So my name is Philipp Hager. This is joint work with Romain de Fayette, Jean-Michel Renders, Onno Suter, and Martin de Rijke. And this is our reproducibility paper titled Unbiased Learning to Rank Meets Reality, Lessons from Baidu's Large-Scale Search Dataset. So not a fairness paper, more unbiased learning to rank for you. So to quickly recap, I think by now it's well established in this session that top-ranked items gather more user attention and thus also more clicks, typically in web search. So the common wisdom is we should not naively interpret clicks and especially non-clicking on an item as positive and negative feedback in this case. And so the domain of unbiased learning to rank deals with kind of how to deal with position bias in this example, for example, when training a new learning to rank algorithm. And most academic work, I would say, in this field is, as we also just saw, is evaluated in simulation because big companies don't like to release their click data that often. And there we take typically classic learning to rank data sets and then simulate synthetic user clicks, which brings us to the question, well, does it actually work in reality, right? Does it actually matter? And we got a little bit of an answer at NeurIPS 2022 from Baidu, and they released a data set which is called Baidu Ultra, and it's the largest kind of web search data set with real clicks for offline evaluation. It's a massive data set. It has 1.2 billion user sessions in it. And they also graciously provided some baseline experiments. So they trained 5 monobird cross-encoders on this data set. They trained on clicks, and then they evaluated on an expert annotated test set. So here we see the performance in terms of DCG, so higher is better here, DCG at 10. And the most left point that we see here is when we apply no position bias correction, meaning we naively interpret click as positive feedback, no click as negative feedback, right? And then we see 4 unbiased learning to rank methods here, which are quite established in the literature. And what is kind of striking looking at this is that none of the position bias correction methods consistently or significantly outperform this naive baseline, right? And this is basically the finding that we try to reproduce in this work. So we look at this NeurIPS paper. Why? Well, first of all, it's just a very striking finding, right? So 4 quite established unbiased learning to rank methods do not outperform a naive baseline on this big data set that just warrants more scrutiny as a big claim. The second thing is there was the wisdom cup on this data set, and participants reported much higher ranking performance using unbiased learning to rank, not using unbiased learning to rank. So in fact, we found in the course of this work that all of the results that I just showed you are significantly worse than random shuffling the test data set. So that hints at quite some problems in the original experiments, I would say. We also found some design decisions that we disagreed with, the way that position bias was not properly estimated in this early work, and we also found quite some data set artifacts that we wanted to clean up when repeating these experiments. And lastly, the results focus mostly on point-wise ranking methods, while a lot of these approaches that I just showed you were suggested for pairwise or listwise settings. So we also really wanted to control for which kind of ranking loss are we using in this setting. This brings me to our research questions in this work. So the first one is quite simple. Well, do these unbiased learning to rank methods work on this data set, right? The second one is what's the impact of different ranking loss functions and different input features on the performance. And lastly, because we looked at BERT-based cross-encoders here, well, what's the effect of applying unbiased learning to rank when training a cross-encoder? Let me briefly introduce you a little bit to the data set. As I mentioned before, it's an absolutely gigantic, for academia at least, data set, I would say. It was sampled from the Baidu search engine in April 2022, and in the training data set, what was basically logged is what the user saw. So the user query, and then mostly the top 10 documents that were displayed to the user. So it's a very similar kind of standard Google, Baidu web search kind of setting as you see here on the right. For testing, we have 7,000 annotated queries, and we got a lot of content features. So we have the search query, we have the title and abstract of documents, however in tokenized forms. To preserve user privacy, we don't have Chinese text here, but things were tokenized with a private vocabulary. This is really important because we can't just download a model from Hugging Face, throw it on here and do this. Baidu released a pre-trained BERT, which we'll also use, but essentially if we want to change something, we need to train from scratch ourselves. But this data set is super interesting because we got a lot of information. We have all of the clicks, we have dwell time, we have skipping behavior, we have presentation features like what types of items were displayed, how large were they displayed on screen, what kind of position. In this work, we solely focus on the query document text, position, and clicks, kind of at the very core of unbiased learning to rank, I would say. There is way more analysis in our paper, but what I want to focus on is on estimating position bias. So we had to estimate position bias on this data set. What I show you here is the performance of 4 different position bias estimation methods. So it's regression expectation maximization, something that was just mentioned, and 3 intervention harvesting estimators. And the dotted line is the average click-through rate that I also show you here. You can read this line here as this plot as after normalization, everybody looks, for example, at the first document, around 70% of people look at the second document, around 40% look at the third document. So while all of these different bias estimation methods use different input features and also different assumptions, they converge to a surprisingly similar position bias estimate on this data set. So we take this as evidence that there seems to be a noticeable position bias in this data set, so we would expect classic unbiased learning to rank methods to really help on this data set. All right, let's talk a little bit about our experimental setup that we reproduced. The first thing is we trained a cross-encoder the same way that Baidu did. A cross-encoder is, in this case, a BERT model where we take the current user query and concatenate this with the title and abstract of each document. We feed this as the input to our BERT. And then we have a masked language modeling loss, first of all, where we reconstruct some masked input tokens. However, we also use the CLS token that encodes the entire sequence, feed it through a feed-forward layer, and then predict basically if this query document pair is relevant or not relevant. In this setting, Baidu pre-trained this ranker on clicks or no clicks. So we have kind of a biased pre-training objective, but we replicated this for simplicity in our work. We train on over 500 million documents. This is more than twice the amount that the original BERT was trained on, and we implemented everything in Hugging Face using JAX because it was way faster for us. And then we also looked at a much smaller data set. So we wanted to conduct way more experiments. We wanted to have proper hyperparameter tuning. We wanted to compare a lot of methods. So we found we wanted to have a much smaller data set to compare more things. So we created a data set of 4 partitions only of Baidu Ultra, which has 2,000 partitions. So this is 2.3 million sessions, around 20 million query document pairs. And we pre-computed query document embeddings now for this setting. What did we use? We used the CLS token released by Baidu. So when you use the original BERT to encode the query document pair, we use the CLS token. We use the CLS token of a BERT that we trained ourselves on this data set. And we use classic learning to rank features, TF-IDF, BM25, query likelihood, and so on. And then on this smaller, what we call re-ranking data set here, we trained very small feed-forward redo networks, which are, I would say, more common in classic unbiased learning to rank, where we have a fixed query document embedding, some layers that were like the width, the depth, dropout, normalization, all of these things were heavily tuned. And then we apply different ranking losses in different groups. So we apply methods based on pointwise binary cross-entropy and unbiased learning to rank methods that build on top of that. And in listwise setting, methods building on top of softmax cross-entropy and lambda rank. So let's get to some results. This is the results that we get when we use the CLS token embedding on this re-ranking data set that was released by Baidu. So the first observation is just DCG-wise, the methods that we compare here, we are very, very close. Even on the small data set, we get very similar results to the original NeurIPS paper, so we know we are kind of in a good range. However, even after all of our tuning and implementing more methods, as I mentioned also in the introduction, so this is random shuffling, we are well below that baseline, right? So these query document embeddings don't just seem very informative. So this is the results on the BERT embeddings that we trained. So first of all, we crossed that random threshold, which is nice. And now we can actually look into research question 1. So does unbiased learning to rank work? The way you read this chart here is we have different colored groups, which are all different ranking loss functions. In blue, we have everything based on binary cross entropy. The most left kind of bar is when we do no bias correction. Then we have a two-tower objective, we have regression EM, and then an IPS method. And then afterwards we have softmax-based methods and lambda rank-based methods. What is quite striking is we have some small improvements from some unbiased learning to rank methods. Some are also significant here. One method is significantly worse also in this setup. However, what is quite striking is the biggest difference is between loss functions, not between using unbiased learning to rank or not using unbiased learning to rank. And in fact, the best results we get here are from just using lambda rank and not using the unbiased lambda rank, or pairwise debiasing as it's also called. Just very briefly, this is on learning to rank features. The results are even more mixed. However, the main finding that the ranking loss matters much more is quite consistent here. This brought us to our third research question. You might be thinking, well, you use these fixed query document embeddings and then you train downstream models on it. Why don't you train the BERT with that? And that's exactly what we did. So we trained 6 BERT models from scratch with and without unbiased learning to rank objectives. In the pointwise setting, we found actually that a two-tower objective significantly improved the DCG and also log likelihood in this setting. However, we found both in the pointwise setting and in the listwise setting that any kind of objective that used inverse propensity scoring, like a normal IPS objective or a DLA objective that was also in the previous talk, really deteriorated performance of this cross-encoder. We don't fully understand yet why, but it needs definitely further investigation, that applying IPS-based unbiased learning to rank too early in this pre-training procedure really seems to hurt performance. Some things I want to discuss is, the first thing is there is a big gulf between ranking performance and click prediction. So far we've been only looking at ranking performance on this expert annotated test set. If we look at click prediction on a test set, we are much better taking position bias into account. Like all of the pointwise unbiased learning to rank methods that actually predict a click really help when it comes to log likelihood. But these improvements really don't transfer one-to-one into better ranking performance. So why might unbiased learning to rank not work in this setting? Well, we cover many hypotheses in our paper. I want to only touch briefly on 3. The first one might be, well, maybe the user behavior is just way more complex than the simple methods that we use here. And that is probably right, but doing some bias correction should be still better than doing no bias correction at all. Then there is a distribution shift between what we train on, what we test on. We train on typically the top 10 documents, which are all quite relevant, and then we test on a much deeper pool, up until the top 1,000 documents. So we confront the models at test time with quite different query document pairs. That can be a big problem. And lastly, we also found quite some evidence between disagreement between what users seem to click on and like and annotators. What are the implications? Well, after all of the cleaning and tuning and re-implementing everything from scratch, we actually arrived at a very similar place like the original authors. So these common unbiased learning to rank methods led to, well, at best, marginal improvements on this largest public unbiased learning to rank datasets. This calls for more investigation in this dataset to actually figure out what are the real-world challenges, which we now need to use to adjust our simulation setups with. We need to better understand unbiased learning to rank and transformers, and we also should talk about how we measure success in unbiased learning to rank, because we get very different models and hyperparameters if we just optimize for click prediction or for ranking performance and annotations. And lastly, I want to highlight, this is only on this data set. We don't question the validity of these methods at all in a different setting. This is only for Baidu Ultra. I want to end with the contributions of this work. First of all of our data is public, especially the 3 smaller, cleaned, and pre-processed Baidu unbiased rank datasets. You can download them from Hugging Face in a few lines of code, and that should really help getting more access to this dataset. All of our methods are implemented in JAX to scale to the size of this dataset. It's available on GitHub. All of our BERT models that we trained you can easily download from Hugging Face, and we released a small library for bias estimation because some of these methods didn't have a public reference implementation. With that, I want to thank you very much for your attention, and I'm happy to take questions.